Good morning, good afternoon, good evening. What's going on? It's yours truly, Professor TK the Chemist, and today I'm here to drop a video that deals with molecular geometry. If y'all don't know what that means, let me explain exactly how it works. Let's get into it. First off, molecular geometry deals with this thing called VSEPR. That's right, y'all, VSEPR. And if you're wondering what VSEPR is, here's the definition. Take a look. All right, you got it? Now, in case you're wondering, all right, how does this relate to chemistry? Let me go ahead and explain to you guys in a very simplistic manner how you can actually apply VSEPR. It's quite simple. All you're doing is seeing which element likes to get the most attention to form this bond. Okay? That's all it is. Which element loves to receive the most attention in order to be the most, let's say, on point element of the party. So if you're going to a party, all right, or as y'all young folks say, the kickback, you want to know, well, who's putting in on this party? I mean, I'm gonna be the host of the party, but who's gonna actually bring stuff to the party so that we can have a nice kickback? Well, that's where the other elements come into play. They're bringing their electrons, aka gifts, to the party in order to make this compound, this relationship work and flow. So I'm going to drop something on you and let's see if you can go. All right, let's go. H2O got a flow, bent like a dancer's pose, with 104.5 degrees between. That's how the angle goes. If CH4 stepped to the floor, how would it stand tall? What's its shape and its angle? Can you recall? Let's see how we can determine what the angle is for CH4. Let's draw it out. Here's CH4. And if you look at your periodic table, I know that each group number represents the number of valence electrons around its element. So if I look at group 1, all the elements in group 1 are going to give up one valence electron. In other words, when we go to that kickback party and we give any element that's part of group 1 to the party, they're going to contribute one valence electron, one gift to the party. Group 2, they all have 2 valence electrons, okay? But now we got to skip groups 3 through 12 because, they got a little bit of issues going on. So we just leave them to the side. But we hop on over to groups 13 through 18. We drop the 1, y'all. And the number that is left over, that's the number of valence electrons that each of those elements will contribute. So group 13, they're going to contribute 3 valence electrons. Group 14, they're going to contribute 4 valence electrons, and so forth until you get full and can't give no more. And that's where you get the octet rule. They're contributing 8. Group 18, all right? So you've got carbon. 1 carbon is going to contribute 4 valence electrons. So 1 element of carbon times 4 valence electrons gives me 4. Hydrogen. There are 4 of those, but they're each going to contribute 1 valence electron. But you're going to have a total of 4 for the hydrogen. 4 plus 4 gives us a total of 8. Now here's some bookkeeping. When we start figuring out who's coming to the kickback party and what they're going to contribute, we need to lay everything out as a bookkeeping process, all right? So that means I'm just going to go ahead and show what carbon said they were going to come in and contribute. And then I'm going to show what each hydrogen said they were contributing. And when we get done, when they come on to the party, we're going to check you off at the door, all right? So here we go. This is how you're going to draw it in. Here's carbon in the middle. Matter of fact, let me go ahead and put a different color so you can see this in action. Here's carbon with 1, 2, 3, and 4 valence electrons. Remember that, all right? So we're going to go ahead and just X that out because we don't need carbon anymore. Carbon is the one that's hosting the party. Remember that. The element with the most valence electrons, the one that needs the most attention, has to go in the middle. So that's where carbon is. In the middle. Now hydrogen, the first hydrogen that knocks on the door, boom, 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 boom. they're coming in with one valence electron. So here you go. And we're going to go ahead and knock that one off. Here comes the next hydrogen with the one that is contributing. We're going to knock that one off. Here comes the next hydrogen with the one that's contributing. We're going to cross that one out. And here comes the last hydrogen with the one that's contributing. Cross that out. And as you can see here, you have a total of 8 valence electrons, yes, but you also have to redraw this picture so that you can replace those pairs of electrons with a dash. That represents a single bond in between each of those elements, okay? So a pair of electrons equals a single bond, 2 pairs of electrons equals a double bond, and 3 pairs of electrons, you got it, it equals a triple bond. So when I redraw this picture, I'm going to have carbon still in the middle, and I'm going to redraw the dash. I'm going to redraw the dots with dashes to represent each of those pairs of electrons. Now, we've got to answer our question. The question was, what's the angle, the shape for this compound? According to my handy dandy chart, if I've got 4 bonds attached to the center element and no non-bonding pairs of electrons on the center element, guess what I got? A tetrahedral shape. So this is a tetrahedral shape. This is the molecular geometry shape and the electron shape, okay? I love to blend hip hop with science so you all can see that the two go hand in hand, okay? So stay tuned for the next compound that we're going to draw out. And if you've got bonds that you want me to try to do, let me know in the comments below. Have a good one.